there are a few things that we need to clean up. Now we have the basics of what's going on with the critical values connection towards the extrema. So what's going to happen if we don't have a continuous function? Well, if we don't have a continuous function, there's not a guarantee that my maximum and minimum values actually have to happen in a way that I want them to. Let's look at this example. This is a piecewise defined function. It has two pieces, one of which is a polynomial, the other is a polynomial. One is defined for x less than or equal to 3. The other is defined for x greater than 3. And we want to find the maximum and minimum values on the interval from 0 to 4. So if you think about what the graph is going to do, when you're less than or equal to 3, this graph is going to be continuous. When you're above 3, this graph is also going to be continuous. The only place it's not continuous is at 3. So what we could do is we could essentially break this thing up into two intervals, one from 0 to 3 and the other from 3 to 4. And if we do that, we can hope to find the maximum and minimum values. Let's go ahead and do that. Let's go ahead and break this g of x into two pieces. One of them is the x squared minus 4x. That works on the interval from 0 up to 3. And we're going to find critical points and endpoints here. So let's start with critical points. Take g prime of x. That's going to be 2x minus 4. Then I set that derivative to 0. Solving for x gives me a critical value of x equals 2. 2 is in my interval. So I'm going to find the critical point. My critical point is going to have an input of 2 and an output of what I get when I plug in 2. So I'm going to plug that into the x squared minus 4x component. So 2 squared minus 4 times 2 gives me a negative 4. Now I have two endpoints of this portion of the interval. So one of the endpoints has an x value of 0. If I plug that in, I get 0, 0. In other words, I get an output of 0. The other endpoint on this mini interval is the 3. So we plug in the 3. 3 squared minus 4 times 3 is negative 3. So on the first interval from 0 to 3, we get 3 points of interest. Then we say, well, 0 to 4 is like from 0 to 3, and then from 3 to 4 again. So we're going to use 5x minus 2 on the interval from 3 to 4. So we kind of do a bit of the same thing. But in this case, we use 5x minus 2. On the interval from 3 to 4. If you take a derivative of 5x minus 2, you just end up with the number 5. If I try to set that equals 0, notice that this can't be solved for x. So that means there's no critical value between 3 and 4. So if you can't get a critical value, we just say that. There's no critical value between 3 and 4. But we still have to check the endpoints of 3 and 4. Now this is going to be a little bit tricky because we're using g of x equals 5x minus 2. The 4, normally, I'd plug in there. So the endpoint where I plug in 4 is perfectly fine. 4 times 5, so 5 times 4 minus 2 gives me an 18. The other endpoint, I have to kind of take with a grain of salt. Let me explain what I mean by that. If I plug in 3 into the 5x minus 2, I get 15 minus 2, which is 13. But I want to point out that this endpoint of the interval on this part is not actually a point on my graph. The equal to sign said use x squared minus 4x. Now I still have to check it. I still have to understand that I need to check this, but also I need to, in the back of my head, not understand that this is not a point on the graph. That means if this happened to have been the biggest number around, I would say that this function doesn't actually have a maximum. That's a little awkward, I know. So we're looking at 5 total points and comparing them, one of which doesn't happen to be on the graph, but that's not a problem for us. So I look and compare at all of these points. I get a critical point of 2, -4, one endpoint of 0, 0, another endpoint of 3, -3, an endpoint of 4, 18, and an endpoint that doesn't exist on my graph of 3, 13. This problem worked out really nice because we can see that the maximum output is the 18, and the minimum output is the -4. So we have a minimum at point 2, -4, and we have a maximum at point 4, 18. So that's how this problem works. Let's look at another scenario. We want to find the maximum and minimum values of the following function on its domain. Now, when it says on its domain, what we mean is what values can I plug in for x? It doesn't take too long to understand that if you plug in an x value, which is bigger than 3, you get the square root of a negative, which doesn't work for graphing. If you plug in a number which is smaller than -3, you also end up with a function that doesn't work. So in order to have function values that are defined, we have to isolate our domain to between -3 and +3. And then, just like everything else, we can figure out critical values and figure out endpoints. The domain is the closed interval from -3 to 3. This means that we're essentially trying to solve the problem of finding the maximum and minimum values of the function on the closed interval from -3 to +3. In this example, we have to take a derivative of the function h. H prime of x is going to be equal to the derivative of a square root. We've dealt with derivatives of these types of functions previously. The way we deal with them is we think of the square root as being to the 1/2 exponent or the 0.5 exponent. And then this is simply a chain rule. 0.5 comes out front. It gets multiplied times the normal inside function to the power 0.5 minus 1. And then I have to multiply that times the derivative of the inside function. The derivative of the inside function is -2x. So the derivative of this 9 minus x squared. I'm going to rewrite that so that it looks a little bit nicer. The derivative of the function is equal to, if I take 0.5 times -2, I get -1. So -1x multiplied times 9 minus x squared raised to the power -0.5. A lot of people don't like negative exponents. And in this case, it's one of the cases where I kind of like to rewrite numerator and denominator. I would get -1x divided by 9 minus x squared to the positive 0.5 exponent. Now, this is a lot, okay? But if you follow along, remember, critical values happen when either my derivative is 0 or where my derivative does not exist. My derivative is 0 when the numerator of a fraction is 0. So if the derivative is 0, that means the numerator of that fraction had to have been 0. The derivative is undefined when the denominator of the fraction is 0. All right. So we're undefined when you're dividing by 0. You get 0 when you multiply by 0. That's kind of how it works. This is going to yield different critical values. One of the critical values happens when x is equal to 0. That comes from when the derivative is 0. When I solve this thing, I can simply square both sides. If I square the right-hand side, squared times 0.5, 2 times 0.5 gives me 1. So you just end up with 9 minus x squared. So 0 equals 9 minus x squared, which means x could have been plus or minus 3. Hopefully you can solve that. Just add x squared to both sides and then take a square root of both sides. So x could either be the positive or the negative 3, or it could be 0. If I look back at my interval, notice the positive and negative 3 were the endpoints. That's not a coincidence. That often happens when you have square roots like this. So we have 3 points to check. One of the points is a critical point. It has an input of 0. If I plug that 0 into my original function, I end up with square root of 9, which is 3. The other 2 points are both critical and endpoints at the same time. One of them, so my first critical and endpoint at the same time, is going to have an input of 3. If you input a 3, you get an output of 0. My other critical and endpoint at the same time has an input of negative 3, and it also has an output of 0 in my original function, in this function here. What's this mean the maximum value is? Well, the maximum is going to happen at the maximum output. That's a 3. So the maximum happens at 0, 3. And then there's a tie at the minimums. We have 2 points which tie for the lowest value, or the lowest output value of my function. 3, 0 and negative 3, 0 tie at the minimum. So that's how you do a problem like this. Most of the time, when we're dealing with polynomials, we don't have an undefined situation. But when we're dealing with rational functions, or when we're dealing with functions with square roots in them, oftentimes we will have function derivatives that could be undefined. So derivatives could be undefined in certain situations. Usually for us, they happen when you're dividing by 0, or when you have a weird square root of a negative. I would like you all to try to find the maximum and minimum values of the given function on the given interval. Push pause on the video, try the problem out, and on the next video, we will do it.